It is real. The black hole is real. We have seen it. Not imagined it. Not guessed at it. Not drawn it on a chalkboard and hoped for the best. We have seen it. In April of 2019, a team of over 200 scientists pointed 8 radio telescopes across the planet at a single point in the sky, 55 million light-years away. And when the data came back, when the numbers were crunched and the image was built, there it was. A glowing ring of superheated gas, swirling at nearly the speed of light, wrapped around a shadow so deep that no light could escape it. The black hole at the heart of the galaxy, Messier 87, 6.5 billion times the mass of our Sun. And it looked exactly the way Einstein's equations said it would look, over 100 years before anyone ever pointed a camera at it. The black hole is real. It is the most terrifying, most beautiful, most confirmed object in the cosmos. And yet, tucked away at its very center, hiding behind a curtain of gravity so thick that nothing can peer through it, sits something that might not be real at all. If you are new here, welcome to Cosmic Drift. If this kind of deep space journey is something you enjoy, tap the like button and subscribe to the channel so you never miss a new video. We have so much more of the universe to explore together, and your support means the world. Now, let us step a little closer to the edge, because here is the twist. While the black hole itself is as real as anything gets in this universe, the thing that supposedly lives at its center, the singularity, might be nothing more than a ghost in the math, a phantom, a place where our equations stop making sense and start spitting out nonsense. And for decades, physicists have been quietly whispering what many of them now say out loud. The singularity is probably not real. It is the place where our best theory of gravity, Einstein's general relativity, breaks down. It is the blank page at the end of the textbook, not a physical thing, not a place you can visit, but a sign that says, in very large letters, we do not know what happens here. And that, in many ways, is more fascinating than the black hole itself. So tonight, we are going on a journey. We are going to peel back the layers of the black hole piece by piece. We are going to understand what we know, what we do not know, and what we are only now beginning to guess. We are going to walk right up to the edge of the event horizon, and we are going to look down, not with fear, but with wonder. Because the story of the singularity is really the story of science itself. It is the story of what happens when the universe hands us a puzzle that our current tools cannot solve. And it is the story of what happens next, when brilliant minds roll up their sleeves and get to work building better tools. Let us begin where all things begin in this story, with gravity. You feel gravity right now. You feel it holding you to your bed, your couch, your chair. You feel it in the weight of your own body. It is, in a sense, the most familiar force in all of nature. You have never known a single moment without it. From the instant you were born to this very second, gravity has been there, pulling you gently toward the center of the earth. And yet, for something so familiar, gravity is deeply strange. It took one of the greatest minds in history just to begin to describe it. In 1687, Isaac Newton gave us his law of universal gravitation. Every object in the universe, he said, pulls on every other object. The strength of that pull depends on two things: how much mass each object has, and how far apart they are. The more massive the objects, the stronger the pull. The closer they are, the stronger the pull. Simple, clean. And for over 200 years, it worked beautifully. It predicted the orbits of planets. It explained why the moon circles the Earth. It told us how to launch rockets and chart the paths of comets. Newton's gravity was a masterpiece, but it was incomplete, because Newton could tell you what gravity does, but he could not tell you what gravity is. He could calculate the pull between two objects, but he could not explain how that pull works. How does the sun, sitting 93 million miles away, reach out and grab the Earth? What is the mechanism? What is the messenger? Newton himself admitted that this was a problem. He called it a great absurdity, and for over 2 centuries, nobody had a better answer, until 1915, when a young physicist named Albert Einstein published his general theory of relativity and changed everything. Einstein did not think of gravity as a force at all. He thought of it as geometry. In his view, space is not just an empty stage on which things happen. Space is a thing, a flexible, stretchable, bendable fabric that responds to the presence of mass and energy. When you place a heavy object on this fabric, the fabric curves, and when another object rolls by, it follows the curve. That is gravity, not a force pulling you down, but the shape of space telling you where to go. The Earth does not pull you toward it. The Earth bends the space around it, and you slide along the curve. This is not a metaphor. This is not a simplification. This is what the math says. Space literally warps in the presence of mass. And here is where things get interesting. Because Einstein's equations do not just describe the gentle curve of space around a planet. They also describe what happens when you push things to the extreme. What happens when you take an enormous amount of mass and squeeze it down into a tiny, tiny space? What happens when the curve of space-time becomes so steep that it folds in on itself? The answer, according to the math, is a black hole. Karl Schwarzschild was the first person to solve Einstein's equations in a way that described this kind of object. And he did it in 1916, just months after Einstein published his theory. Schwarzschild was a German physicist serving on the Eastern Front in the First World War, and between artillery bombardments, he sat down and worked out the math. What he found was startling. His solution predicted a region of space where gravity becomes so intense that nothing, not even light, can escape. If you compressed any amount of mass below a certain radius, now called the Schwarzschild radius, you would create a point of no return, a boundary. Cross that boundary and you are done. No engine, no rocket, no force in the universe can bring you back. That boundary is the event horizon, and the object it surrounds is what we now call a black hole. Schwarzschild died in 1916, the same year his solution was published. He never lived to see the full weight of what he had found, and honestly, at the time, most physicists did not take the idea seriously. Einstein himself was skeptical. He thought the math was interesting but doubted that nature would ever actually produce such a thing. A region of space where the laws of physics hit a wall. It sounded more like a mathematical curiosity than a real object. Surely something would prevent it from forming. Surely nature had a safety switch. But nature, as it turns out, does not always come with a safety switch. Through the middle decades of the 20th century, physicists slowly began to realize that black holes were not just possible. They were inevitable. When a massive star runs out of fuel, when the nuclear furnace at its core goes quiet, there is nothing left to hold the star up against its own gravity. And if the star is heavy enough, much heavier than our sun, the collapse cannot be stopped. Not by the pressure of electrons, not by the pressure of neutrons, not by anything. The star falls in on itself faster and faster, and as it does, it crosses below its own Schwarzschild radius. An event horizon forms, and just like that, a black hole is born. By the 1960s and 1970s, the golden age of black hole research was in full swing. Physicists like Roger Penrose, Stephen Hawking, and Roy Kerr were exploring the math with new tools and new ideas. Kerr, in 1963, found the solution for a rotating black hole, which is the kind that actually exists in nature, since all real objects spin. Penrose, in 1965, proved something remarkable. Using a set of powerful mathematical theorems, he showed that once a star crosses that threshold, once it collapses past its event horizon, a singularity is guaranteed. No matter what the star does on the way down, no matter how it twists or turns, the math says it must end up as a singularity, a point of infinite density, a place where all the mass of the star is crushed into zero volume. Penrose won the Nobel Prize in Physics in 2020 for this work, and his proof has stood for over 50 years. But here is the thing. The singularity is not a triumph of physics. It is a failure. It is the place where Einstein's beautiful theory of gravity throws up its hands and says, "I cannot do this anymore. I cannot describe what happens here." Let us be very clear about what a singularity actually is, because the word gets thrown around a lot, and it is easy to misunderstand. A singularity, in mathematics, is simply a point where a function becomes undefined. You have probably seen this in basic math. Take the function y equals 1 divided by x. You can plug in any number for x and get a sensible answer, except 0. When x equals 0, the function gives you 1 divided by 0, which is undefined. It does not equal some enormous number. It does not equal infinity, not really. It is just broken. The equation has no answer. That is a singularity, a place where the math stops working. Now, in the context of a black hole, the singularity is the point where the equations of general relativity produce this same kind of breakdown. As matter collapses inward, the density increases, and the curvature of spacetime becomes more and more extreme. And according to the math, at the very center, the density becomes infinite, and the curvature becomes infinite. Every number in the equation blows up. The answer, if you can call it that, is infinity. And in physics, infinity is almost never the right answer. Infinity is a red flag. Infinity is a neon sign that says your theory is missing something. Think about it this way. If a theory tells you that the temperature of a cup of coffee is infinite, you do not conclude that the coffee is infinitely hot. You conclude that your thermometer is broken, and that is exactly what is happening with the singularity. General relativity is an astonishingly good theory. It has been tested and confirmed in countless experiments. It predicted gravitational waves, which we have now detected. It predicted the bending of light around massive objects, which we have now photographed. It predicted the existence of black holes, which we have now imaged. But at the center of a black hole, the theory breaks. It gives us infinity, and infinity is not a thing. It is a confession. It is the theory telling us, I do not know what happens here. You need a better theory for this part. And this is not the first time something like this has happened in the history of physics. In fact, it has happened before, in almost exactly the same way. At the beginning of the 20th century, physicists were trying to understand how hot objects radiate energy. They had a formula, and the formula worked beautifully for most wavelengths of light. But when they pushed it to the extreme, when they tried to calculate the energy at very short wavelengths, the formula gave them infinity. It said that any hot object should be radiating an infinite amount of energy at ultraviolet wavelengths. This was obviously wrong. They called it the ultraviolet catastrophe. And for a while, nobody knew how to fix it. Then Max Planck came along and proposed something radical. What if energy is not continuous? What if it comes in tiny discrete packets, which he called quanta? It was a wild idea. It went against everything physicists thought they knew about the nature of energy. But it worked. The infinity disappeared. The formula made sense again. And that single idea, the quantum, gave birth to an entirely new branch of physics. Quantum mechanics, one of the most successful theories in the history of science. The lesson here is profound. When a good theory gives you infinity, it does not mean the universe is infinite. It means the theory has reached its limit. It means there is a deeper, more complete theory waiting to be discovered. And that is exactly where we find ourselves with the singularity. General relativity gives us infinity at the center of a black hole. And the fix, almost certainly, is the same kind of fix that solved the ultraviolet catastrophe. We need a deeper theory. We need a theory that combines gravity with quantum mechanics. We need a theory of quantum gravity. But we are getting ahead of ourselves. Before we dive into what might replace the singularity, let us take a closer look at the black hole itself, because the black hole is a lot more than just its center. And to understand why the singularity is probably wrong, we first need to understand the anatomy of the thing that supposedly contains it. Picture a black hole, not the Hollywood version, not the dramatic swirling disk from a movie. Picture the real thing, as described by the math. At its heart, the simplest kind of black hole has two main features, the event horizon and, supposedly, the singularity at the center. That is it. Two things. One of them is real and well understood. The other is a question mark. The event horizon is the outer boundary. It is the point of no return. And it is important to understand that the event horizon is not a physical surface. It is not a wall. It is not a shell. You cannot touch it. You cannot see it. If you were falling toward a black hole, you would cross the event horizon without even knowing it. There would be no flash of light, no loud noise, no physical sensation of crossing a boundary. You would simply drift past an invisible line in space, and from that moment on, your fate would be sealed. You could fire every rocket you have. You could point yourself directly away from the center, and it would not matter. Because inside the event horizon, the very geometry of space and time has been twisted so thoroughly that every possible direction, every possible path you could take, leads deeper into the black hole. It is not that the gravity is too strong for you to escape. It is that the concept of escape no longer exists. Inside the event horizon, moving away from the singularity is like trying to move backward in time. It is simply not a thing that space-time allows. This is one of the strangest ideas in all of physics, and it comes directly from Einstein's equations. Inside the event horizon, the roles of space and time actually swap. What was once a direction in space, the direction pointing toward the center, becomes the direction of time. And just as you cannot stop moving forward in time in your everyday life, you cannot stop moving toward the center once you are inside the event horizon. Your future is the singularity, or at least that is what the math says. From the outside, the event horizon is almost invisible. If you were watching from a safe distance, you would see something remarkable. You would see matter spiraling inward, getting faster and hotter as it approaches the edge. Gas and dust, and even entire stars can be caught in this spiral, forming a brilliant glowing disk called an accretion disk. The temperatures in this disk can reach billions of degrees. The particles are moving at nearly the speed of light, and as they crash and grind against each other, they release enormous amounts of radiation. X-rays, gamma rays, visible light, This is the light we actually see when we look at a black hole. We are not seeing the black hole itself. We are seeing the chaos around it. The event horizon casts a shadow, a dark region at the center of all that light, and that shadow is what the Event Horizon Telescope captured in 2019. The image of the black hole in Messier 87 was a triumph. It was the culmination of decades of work by hundreds of scientists across the globe. 8 radio telescopes spread across the planet were synchronized to the precision of an atomic clock. The data was so vast that it could not be sent over the internet. It had to be physically shipped on hard drives to be processed. And when it was all assembled, the result was exactly what general relativity had predicted. A bright ring of light, slightly brighter on one side because the black hole is spinning, surrounding a dark central shadow. The shape was right. The size was right. Einstein's theory, written over a century earlier, had nailed it. 2 years later, in 2022, the same team released an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, 4 million times the mass of our Sun, sitting just 26,000 light-years away, close enough that the stars in our galaxy orbit around it, close enough that we can track individual stars as they whip around the dark center at thousands of miles per second. And again, the image matched the prediction. A glowing ring, a dark shadow, the fingerprint of an event horizon. So the event horizon is real. The black hole, as an object, is confirmed. There is no serious scientific debate about this anymore. We have seen it. We have measured it. We have detected the gravitational waves produced when 2 black holes collide and merge, rippling the fabric of spacetime itself. LIGO, the Laser Interferometer Gravitational Wave Observatory, first detected these waves on September 14, 2015. 2 black holes, about 36 and 29 times the mass of our Sun, spiraling into each other over 1 billion light-years away, crashing together in a fraction of a second, converting about 3 solar masses of material directly into gravitational energy. The signal matched general relativity's predictions with extraordinary precision. Since that first detection, hundreds of black hole mergers have been observed. The black hole is as real as the ground beneath your feet. But the singularity is a different story entirely. Remember, the singularity is what the math predicts at the very center of a black hole. It is the endpoint of the collapse, the place where all the matter ends up. And according to general relativity, that place is a point of 0 volume and infinite density. All the mass of the star, everything that ever fell in, crushed into a space smaller than an atom, smaller than a proton, smaller than anything. Infinitely small, infinitely dense. And that is where things fall apart, not just physically, but mathematically. Because if you think about it, the idea of infinite density does not actually make sense. The mass of the black hole is finite. We can measure it. Messier 87's black hole has a mass of 6.5 billion suns. That is a lot, but it is a number. It is not infinity. So how can a finite amount of mass have infinite density? Only if it occupies 0 volume. And 0 volume is not a physical thing. It is a mathematical abstraction. In the real world, things have size. Even the tiniest particles we know of, quarks and electrons, occupy space. Maybe not much space, but some. The idea that all the mass of a star can be compressed into literally no space at all is not a physical prediction. It is a mathematical artifact. It is what happens when you push a theory past the point where it applies. And here is the key point, the thing that separates the event horizon from the singularity. The event horizon is a prediction of general relativity that has been tested and confirmed. We can see its effects. We can measure its size. We can photograph its shadow. The singularity, on the other hand, is a prediction of general relativity that cannot be tested because it is hidden behind the event horizon. No information can escape from inside a black hole. No light, no signal, no data of any kind can cross the event horizon from the inside and reach us on the outside. This means we cannot observe what is happening at the center. We cannot run experiments. We cannot take measurements. The singularity exists only in the math. And the math, as we have discussed, is telling us something is wrong. This brings us to one of the most famous ideas in black hole physics, the cosmic censorship hypothesis proposed by Roger Penrose in 1969. Penrose noticed that while the math predicted singularities, those singularities were always hidden behind event horizons. Nature, it seemed, was being modest. It was wrapping every singularity in a cloak of invisibility, making sure that the place where the laws of physics break down could never be seen by an outside observer. Penrose suggested that this might be a rule, a law of nature. Every singularity must be hidden. No naked singularities allowed. It is an elegant idea, and it has held up remarkably well. But notice what it implies. If nature has to hide the singularity behind an event horizon, if the breakdown of the equations must be kept out of sight, perhaps that is because the singularity is not actually there. Perhaps the cosmic censorship hypothesis is not protecting us from a real thing. Perhaps it is protecting us from a mathematical mistake. And this is where the story starts to get really interesting. Because over the last few decades, a growing number of physicists have been asking a very simple question. What if the singularity is not real? What if, instead of a point of infinite density at the center of a black hole, there is something else entirely? Something dense, yes. Something extreme, absolutely. But something finite. Something physical. Something that makes sense. The answer, almost everyone agrees, lies at the intersection of two great theories: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which describes the behavior of matter at the smallest scales. These two theories are the pillars of modern physics. They are both spectacularly successful in their own domains. General relativity tells us how planets orbit, how galaxies form, how the universe expands. Quantum mechanics tells us how atoms work, how light behaves, how the chemistry of life is possible. But there is a problem, a big one. These two theories do not get along. General relativity is a smooth, continuous theory. It describes spacetime as a fabric that bends and flows without any gaps or jumps. Quantum mechanics, on the other hand, is a chunky, probabilistic theory. It says that at the smallest scales, things are not smooth at all. Energy comes in packets. Particles exist in clouds of probability. Nothing is certain until it is measured. And when you try to combine these two theories, when you try to apply quantum rules to gravity, the math explodes. You get infinities everywhere, nonsensical answers, gibberish. This is the great unsolved problem of modern physics, the search for a theory of quantum gravity, a single unified framework that describes both the very large and the very small, the very heavy and the very light, the curvature of spacetime and the uncertainty of particles. We do not have this theory yet, but we have strong candidates, and those candidates have something very interesting to say about the singularity. The first and perhaps most developed candidate comes from a framework called loop quantum gravity. Loop quantum gravity, or LQG for short, takes Einstein's general relativity as its starting point and tries to apply the rules of quantum mechanics directly to the fabric of spacetime itself. The core idea is simple but radical. What if space is not smooth? What if, at the very smallest scales, space is made up of tiny, discrete chunks, not atoms, not particles, but tiny loops of gravitational field, woven together like a fabric, each one carrying a tiny quantized unit of area and volume. If this is true, then space has a minimum size. You cannot divide it forever. You cannot squeeze something into a volume smaller than the smallest possible loop. And if space has a minimum size, then the singularity cannot exist, because the singularity requires matter to be compressed into zero volume. And in loop quantum gravity, zero volume is not allowed. There is a flaw. A quantum flaw. And when the collapsing star hits that flaw, instead of continuing to crush down forever, something else happens. Something pushes back. This is one of the most beautiful ideas in modern physics. In loop quantum gravity, when matter is compressed to extreme densities, when it approaches what is called the Planck density, a quantum repulsive force kicks in. Not a force from particles or fields, but a force from the fabric of spacetime itself. The quantum nature of space resists further compression. It pushes back, and it pushes back hard enough to stop the collapse. No singularity forms. Instead, the collapsing matter bounces. Think of it like squeezing a spring. The harder you push, the harder it pushes back. And at some point, no matter how strong you are, the spring will stop compressing and start pushing outward. In loop quantum gravity, spacetime is the spring, and the bounce is a real physical event. The matter does not collapse to a point. It collapses to an incredibly small, incredibly dense, but finite object, and then it starts to expand again. This idea was formalized in 2014 by two physicists, Carlo Rovelli and Francesca Vidotto. They proposed that at the center of every black hole, instead of a singularity, there is an object they called a Planck star. The name comes from the Planck scale, which is the scale at which quantum gravitational effects become important. The Planck length is about 10 to the negative 35 meters. To give you a sense of how small that is, imagine you took a single atom and stretched it to be the size of the entire observable universe. The Planck length on that scale would be about the size of a tree. That is how tiny we are talking about. But the key insight is that the Planck star is not actually that small. The repulsive force kicks in well before the matter reaches the Planck length. For a stellar mass black hole, the Planck star would be roughly the size of a trillionth of a meter, still impossibly small by everyday standards, but infinitely larger than the zero volume that a singularity would require. And that makes all the difference. The Planck star is not infinitely dense. It is extremely dense, yes, but its density is finite. It has a real physical volume. And because it is not a singularity, it does not produce the mathematical breakdown that has haunted black hole physics for decades. The equations make sense. The numbers are large, but they are numbers, not infinities. And the physics works. But there is a twist. A wonderful, mind-bending twist. The bounce, from the star's own perspective, happens almost instantly. The matter collapses, hits the quantum floor, and bounces back in a flash. But from the outside, from our perspective, the bounce appears to take an unimaginably long time. This is because of gravitational time dilation, one of the strangest consequences of general relativity. Time runs slower in strong gravitational fields, and the gravitational field near a black hole is so strong that the time dilation is extreme. What takes a fraction of a second inside the black hole appears, from the outside, to take billions of years, perhaps even 14 billion years, roughly the current age of our universe. This means that even the oldest black holes, the ones that formed in the very earliest days of the cosmos, may only now be starting to bounce. They are not eternal. They are not permanent. They are, in a sense, frozen in mid-bounce, caught in the act of rebounding, but slowed down to a crawl by the warp time around them. And as the black hole slowly loses mass through Hawking radiation, the event horizon gradually shrinks, and eventually the bounce catches up. The Planck star inside meets the shrinking event horizon, and in a final burst, all the information that was ever trapped inside is released back into the universe. No information is lost. No paradox remains. This is, for many physicists, a profoundly satisfying picture. It solves the singularity problem. It addresses the information paradox, one of the deepest puzzles in all of physics. And it does it all within a framework that respects both general relativity and quantum mechanics. But the Planck star is not the only idea on the table. There is another, very different proposal coming from a very different corner of theoretical physics, and it involves strings. String theory is the other major candidate for a theory of quantum gravity. If loop quantum gravity builds on Einstein's general relativity and quantizes spacetime, string theory takes a different approach. It starts from quantum mechanics and rebuilds gravity from the ground up. The basic idea is that the fundamental constituents of the universe are not point-like particles. They are tiny, vibrating strings of energy. Different vibrations produce different particles. One vibration mode gives you an electron. Another gives you a quark. Another gives you a photon. And one particular vibration mode gives you the graviton, the hypothetical particle that carries the gravitational force. In this picture, gravity is not a property of spacetime. It is a property of strings. String theory is a vast and complex mathematical framework. It requires extra dimensions of space, usually 10 or 11, most of which are curled up so small that we cannot detect them. It predicts a dizzying array of new particles and phenomena, and while it has produced some astonishing mathematical results, it has not yet made a testable prediction that has been confirmed by experiment, so it remains a theory in the truest sense of the word, a work in progress. But when string theorists turned their attention to black holes, they found something remarkable. They found that in string theory, the singularity at the center of a black hole is replaced by something they call a fuzzball. The fuzzball idea was developed primarily by Samir Mathur, a physicist at Ohio State University, starting in the early 2000s. In string theory, matter is made of strings, and when a star collapses to form a black hole, those strings do not all get crushed into a single point. Instead, they get compressed and tangled together into a vast, extended object, a ball of strings, a fuzzball. This fuzzball fills the entire region that we would normally think of as the inside of the black hole, from the center all the way out to where the event horizon would be. In the fuzzball picture, there is no empty interior. There is no singularity. There is not even, strictly speaking, a true event horizon. Instead, there is a surface. A fuzzy quantum surface made of tangled strings. When something falls into a black hole, it does not plunge through an event horizon into empty space and then crash into a singularity. It falls onto this surface and gets absorbed into the fuzzball. Its strings merge with the strings of the fuzzball, and all the quantum information about the infalling object is preserved, encoded in the larger, more complex tangle of strings. This is a radically different picture of a black hole. In the traditional view, a black hole is mostly empty. A thin event horizon surrounds a vast void with a tiny, infinitely dense point at the center. In the fuzzball view, the black hole is full. It is a solid, or at least solid-like object. Dense, yes, incredibly so, but not infinitely dense, and not compressed to a point. The fuzzball has a real size. And that size turns out to be exactly equal to what we would normally calculate as the Schwarzschild radius, the radius of the event horizon. This is a remarkable result. Two completely different mathematical approaches, Schwarzschild's classical calculation from 1916 and Mather's string theory calculation from the 2000s, arrive at the same size for the black hole. One describes the event horizon, the other describes the fuzzball surface, and they match. From the outside, a fuzzball would look almost exactly like a classical black hole. It would have the same mass, the same gravitational pull, the same effect on nearby stars and gas. Light passing close to it would bend in the same way. Stars orbiting it would move in the same paths. For almost all practical purposes, you could not tell the difference. The only place where the two pictures diverge is at the quantum level, and the difference matters enormously for one particular problem: the information paradox. The information paradox is one of the great unsolved problems of physics. It was first identified by Stephen Hawking in the 1970s. Hawking discovered, through a brilliant piece of theoretical work, that black holes are not entirely black. They emit radiation, a faint thermal glow, now called Hawking radiation, produced by quantum effects near the event horizon. This radiation carries energy away from the black hole, which means the black hole is slowly losing mass. Over time, an incredibly long time for any large black hole, but still a finite time, the black hole will shrink, and eventually it will evaporate completely. It will be gone. Now here is the problem. The Hawking radiation is thermal. It is random. It carries no information about what fell into the black hole. It is like the heat coming off a campfire. The heat does not tell you what kind of wood you burned. It does not tell you what shape the logs were, or what color, or how they were stacked. The information about the wood is gone, destroyed by the fire. And if the same is true for a black hole, if the Hawking radiation really carries no information, then when the black hole finally evaporates, all the information about everything that ever fell in is lost, gone from the universe, forever. And that is a huge problem, because one of the most fundamental laws of quantum mechanics says that information cannot be destroyed. It can be scrambled. It can be hidden. It can be made extremely difficult to recover, but it cannot be erased from existence. Every quantum process is, in principle, reversible. You should always be able to figure out what happened in the past by looking at the present. Destruction of information violates a principle called unitarity, which is the bedrock of quantum mechanics. If unitarity fails, quantum mechanics fails. And if quantum mechanics fails, then essentially all of modern physics falls apart. So either Hawking radiation carries information, and we just do not understand how, or the black hole does not actually destroy information, and there is some mechanism that preserves it. For decades, this paradox drove physicists to distraction. Hawking himself initially argued that information was truly lost, and that quantum mechanics needed to be modified. Most other physicists disagreed. They believed that information must be preserved somehow, but nobody could explain how. The fuzzball proposal offers a clean solution. If a black hole is a fuzzball, then there is no empty interior where information can get trapped. The information of everything that falls in is spread across the fuzzball surface, encoded in the quantum states of the tangled strings. When the fuzzball emits Hawking radiation, that radiation is not truly thermal. It is not random. It carries subtle correlations that encode the information. Just as the heat from a burning book, if you could measure every single photon and particle with perfect precision, would in principle tell you what was written on the pages, the Hawking radiation from a fuzzball carries a faint but real imprint of everything that went in. Information is preserved. Unitarity is saved. The paradox is resolved. Now, it is important to be honest. Neither the Planck star nor the fuzzball has been experimentally confirmed. We cannot look inside a black hole. We cannot directly test what happens at the center. These are theoretical proposals, supported by mathematics, but not yet by observation. And there are other proposals too. Gravastars, which are hypothetical objects where the collapse is halted by a kind of quantum vacuum energy. Dark stars, where a Planck core replaces the singularity. The Haywood metric, which is the simplest mathematical solution to general relativity that allows a black hole without a singularity. Each of these ideas approaches the problem from a slightly different angle, but they all share the same core conclusion. The singularity is not real. Something else is there. In early 2025, a team of physicists from the University of Barcelona published a paper that added significant weight to this view. Pablo Bueno, Pablo Cano, and Robbie Henniger showed that black holes without singularities can form from pure gravity alone, without the need for exotic matter. Previous models of singularity-free black holes often required unusual types of matter with strange properties to make the math work. This new model does not. It uses only modifications to Einstein's equations that arise naturally from quantum gravity. The equations are clean, the physics is consistent, and the black holes they describe obey the laws of thermodynamics, which gives the model additional credibility. One of the researchers, Robbie Henniger of Durham University, put it simply: if black holes do not have singularities, then they are much more ordinary. They are still extreme. They are still bizarre by everyday standards, but they are not magical. They are not places where the laws of physics give up. They are simply the most extreme objects that the laws of physics allow, and that, in many ways, is a more satisfying picture of the universe. A universe where the rules hold, even in the most extreme conditions. A universe without mathematical breakdowns. A universe that makes sense all the way down. But let us go even deeper, because the question of what replaces the singularity is not just an abstract theoretical puzzle. It connects to some of the deepest and most fundamental questions we can ask about the nature of reality. Consider space. Consider time. Consider what they actually are. In our everyday experience, space and time feel smooth and continuous. You can move a little bit to the left, then a little bit more, then a little bit more. There seems to be no limit to how finely you can divide space. The same is true of time. You can measure a second, a millisecond, a nanosecond, a picosecond. There always seems to be a smaller interval. But what if that is an illusion? What if, at the very smallest scales, space and time are not smooth at all? What if they are grainy, pixelated, made up of tiny, discrete units, like the pixels on a screen? This is what many approaches to quantum gravity suggest. Below the Planck length, roughly 10 to the negative 35 meters, the very concept of smooth spacetime may break down. At that scale, the quantum fuzziness of the universe takes over. Space is not a fabric anymore. It is a foam, a bubbling, fluctuating, constantly shifting quantum foam where distances and durations lose their ordinary meaning. And if space is quantized, if it comes in minimum-sized chunks, then the singularity literally cannot exist. You cannot compress matter into a space smaller than the smallest possible space. The singularity requires zero volume, and quantum gravity says the minimum volume is not zero. It is small, unimaginably small, but it is not zero. And that tiny, crucial difference is the difference between a universe with singularities and a universe without them. This is why the singularity problem is not just a problem about black holes. It is a problem about the nature of space-time itself. Solving it would tell us something profound about the fabric of reality. It would tell us whether space is truly continuous, like a smooth sheet of glass, or discrete, like a mosaic made of incredibly tiny tiles. And the answer to that question would reshape our understanding of everything. Not just black holes, not just gravity, but the very structure of the universe. And there is another connection, equally deep and equally fascinating. The singularity at the center of a black hole is not the only singularity in physics. The Big Bang itself is a singularity. According to general relativity, if you trace the expansion of the universe backward in time, everything gets closer together. The density increases, the temperature rises, and at the very beginning, roughly 13.8 billion years ago, all the matter and energy in the observable universe was compressed into a single point of infinite density and infinite temperature. A singularity. The same kind of mathematical breakdown that appears at the center of a black hole appears at the birth of the universe. And the same solution likely applies. If the singularity at the center of a black hole is replaced by a Planck density core, then the singularity at the beginning of the universe is probably replaced by a similar quantum bounce. The universe may not have begun with a true singularity. It may have bounced. This idea, explored in loop quantum cosmology, suggests that our universe may have emerged from the collapse of a previous universe. At the moment of maximum compression, when the density hit the Planck threshold, the quantum repulsive force kicked in, and the collapse reversed. What we call the Big Bang may actually be a big bounce. Not the beginning of everything, but a transition from one state to another, a cosmic rebirth. If this is true, then black holes and the Big Bang are fundamentally the same kind of event. Both involve the extreme compression of matter and energy. Both are predicted by general relativity to produce singularities. And both are likely resolved by quantum gravity in the same way, by replacing the singularity with a finite, physical, quantum gravitational state. The universe, it seems, has a consistent plan, a set of rules that hold everywhere, at every scale, in every circumstance, even at the center of a black hole. Even at the beginning of time. Let us pause here for a moment and take a breath. We have covered a lot of ground. We have traveled from the surface of the Earth, through Newton's gravity, through Einstein's curved spacetime, past the event horizon, and into the very heart of a black hole. And what we have found is not what most people expect. Most people think the story of a black hole ends with the singularity, with that terrifying, impossible point of infinite density. But the real story is just beginning, because the singularity is not the answer. It is the question, and the question it asks is the most important question in all of physics. What happens when gravity meets the quantum world? Let us explore this question from yet another angle, because there is a beautiful mathematical approach that strips the problem down to its bare essentials. It is called the Haywood metric, and it was proposed by physicist Haywood. The idea is elegant in its simplicity. Take the standard equations of general relativity, the same equations that predict the Schwarzschild black hole, the same equations that predict the event horizon and the singularity, and add one constraint, just one. Singularities are not allowed. That is it. That is the entire modification. You take Einstein's equations and you say, whatever solution you give me, it cannot contain a singularity. The math still has to work. The solution still has to describe a static, spherically symmetric region of curved spacetime. It still has to match all the observations we have of black holes from the outside. But it cannot have a point of infinite density at the center. And when you apply this constraint, the equations give you a perfectly valid solution. A black hole that looks exactly like a Schwarzschild black hole from the outside, with the same event horizon, the same gravitational pull, the same shadow. But at the center, instead of a singularity, there is a smooth, finite region of extremely curved spacetime, a core of immense density, but not infinite density. The curvature of spacetime reaches a maximum value and then levels off. It does not blow up to infinity. It plateaus. For supermassive black holes, the difference between a Haywood black hole and a Schwarzschild black hole is so tiny that we could never detect it with current technology. The event horizon is the same size. The shadow is the same shape. The gravitational waves are the same frequency. From the outside, there is no way to tell them apart, and that is actually a point in favor of the Haywood metric. It is consistent with every observation we have ever made. It does not require new particles or new fields or new dimensions. It just requires that the universe does not allow infinities. And as we discussed earlier, the universe has a very long track record of not allowing infinities. The catch, of course, is that the Haywood metric does not explain why singularities are banned. It just assumes they are. It does not provide a physical mechanism for what stops the collapse. It is a mathematical framework, not a physical theory. And that is where the quantum gravity approaches, like loop quantum gravity and string theory, come in. They provide the mechanism. They explain the why. The Haywood metric describes the shape of the answer. Quantum gravity provides the substance. Now, you might be wondering, if so many physicists think the singularity is not real, why was Roger Penrose given the Nobel Prize for proving that singularities form in black holes? It is a fair question, and the answer is subtle but important. Penrose did not prove that singularities exist in nature. He proved that general relativity predicts singularities. That is a different thing. Penrose showed that within the framework of classical general relativity, if certain reasonable physical conditions are met, then a singularity must form. His theorems are airtight. They are mathematically rigorous. They have been checked and verified by generations of physicists. And they tell us something crucial. They tell us that general relativity, by itself, predicts its own failure. They tell us that the theory of gravity, taken to its logical conclusion, produces a result that cannot be physical. And that is an enormously important result because it tells us, with mathematical certainty, that general relativity is incomplete, that something more is needed. Penrose himself has always been careful about this distinction. He knows that his theorems assume classical general relativity and nothing more. He knows that in a quantum theory of gravity, the assumptions of his theorems may not hold. And he has acknowledged that the singularity may not exist in the physical universe. His theorems are not a statement about reality. They are a statement about a theory. And the statement is this: if general relativity is the whole story, then singularities are inevitable. But general relativity is almost certainly not the whole story. There is a quantum chapter, and in that chapter, the ending may be very different. This is a point worth emphasizing because it gets at the heart of how science works. Science does not deal in absolute truths. It deals in models, frameworks, approximations that are progressively refined over time. Newton's gravity was a brilliant model that worked for over 200 years. Then Einstein came along and showed that it was an approximation of a deeper reality. Einstein's general relativity is a brilliant model that has worked for over 100 years. And now we are beginning to see that it too is an approximation. Not wrong, not useless, incredibly, astonishingly accurate in its domain, but incomplete, missing a piece. And the singularity is the signpost that tells us where the missing piece fits. Roy Kerr understands this better than perhaps anyone alive. Kerr is the physicist who, in 1963, discovered the solution to Einstein's equations for a rotating black hole. His solution, the Kerr metric, is the foundation of modern black hole physics. Every real black hole we observe is described by some version of the Kerr metric, and in 2023, at the age of 89, Kerr published a new paper in which he challenged the very idea of singularities. Using careful mathematical arguments, he showed that the assumptions underlying Penrose's singularity theorems may not apply to realistic, rotating black holes. He argued that the matter falling into a black hole may not actually be forced to reach a singularity. Instead, it might avoid the singular point entirely, spiraling around it or passing through it into something else. The details are complex and technical, and the debate is ongoing. But the message is clear. Even the man who wrote the equation for the most realistic black hole model we have does not believe that singularities are physical. Let us now zoom out from the math and the theory and think about why this question matters to us. As human beings, why does the singularity capture our imagination? Why does the idea of a point of infinite density, hidden behind an impenetrable curtain, feel so compelling? Part of it, certainly, is the drama. The singularity is the ultimate mystery. It is the one place in the universe where we truly do not know what is happening. It is the frontier of human knowledge, and something about that frontier calls to us. But there is something deeper going on. The singularity speaks to a very old and very human fear, the fear of the unknown, the fear that there are places in the universe that we can never understand, places where the rules break down and chaos reigns. The singularity, in its traditional form, is a kind of cosmic monster, a place where physics itself dies, where cause and effect lose their meaning, where the rational, orderly universe we depend on dissolves into nonsense. That is a frightening idea, and it is no wonder that it has captured our collective imagination. But here is the thing. The new physics, the physics of quantum gravity, is telling us a very different story. It is telling us that the monster is not real, that the breakdown is not in nature. It is in our equations. The universe is not chaotic at the center of a black hole. Our description of it is. And when we build a better description, the chaos disappears, the monster evaporates, and what we find instead is something beautiful. Not a point of infinite density and zero sense, but a finite, physical, comprehensible object, dense beyond imagination, curved beyond anything in our everyday experience, but knowable, understandable, part of the same orderly universe that produced stars and planets and life. That is a profoundly hopeful message. It tells us that the universe is not hiding secrets behind impenetrable walls. It is hiding them behind problems that we have not yet solved. And the difference between a wall and a problem is everything. Walls stop you. Problems invite you. And the best physicists alive are accepting that invitation. Let us talk now about what we might be able to observe, because physics, at the end of the day, is an experimental science. Theories are beautiful, but they must be tested. And while we cannot look inside a black hole, there may be ways to figure out what is happening at the center by studying what happens at the edge. Gravitational waves are our best tool for this. When two black holes merge, they produce gravitational waves, ripples in spacetime that travel across the universe at the speed of light. These waves carry information about the merging black holes, their masses, their spins, their orbits, and crucially, their internal structure. If black holes have singularities at their centers, the gravitational waves they produce will have a specific pattern. If they are fuzzballs, or Planck stars, or some other kind of singularity-free object, the pattern will be slightly different. The differences are incredibly subtle, but as our detectors get more sensitive, we may be able to detect them. LIGO has come a long way since its first detection in 2015. The detectors have been upgraded multiple times. New detectors have joined the network. Virgo in Italy, Kagra in Japan, and the results have been extraordinary. Hundreds of black hole mergers have been observed. In January 2025, LIGO detected the clearest gravitational wave signal ever recorded from a black hole merger designated GW25514. The signal was so clean, so precise, that scientists were able to identify the first overtone of the merging black hole's ringdown, the vibration pattern it produces as it settles into its final state. This was a landmark result. It confirmed predictions made by general relativity with unprecedented precision. And it laid the groundwork for future measurements that could, in principle, reveal deviations from the classical model. Deviations that might tell us what is really happening inside. The idea is this. When two black holes merge, the newly formed black hole vibrates, like a bell that has been struck. These vibrations gradually die out as the black hole radiates gravitational waves and settles into a stable state. This process is called ringdown. The pattern of the ringdown depends on the properties of the black hole, its mass, its spin, and crucially, its internal structure. A classical black hole with a singularity will produce a specific ringdown pattern. A fuzzball, or a Planck star, or any other singularity-free object will produce a slightly different pattern. The differences are expected to show up in the late-time behavior of the signal. After the initial burst fades, there may be faint echoes, tiny reverberations caused by the gravitational waves bouncing around inside the modified interior of the black hole. These echoes would be like the ringing of a hollow drum versus a solid one. A singularity, being a mathematical point, would not produce echoes. A solid interior would. Searching for these echoes is one of the most active areas of research in gravitational wave astronomy today. So far, no definitive echoes have been found. The signals we have detected are all consistent with classical black holes, but the sensitivity of our detectors is still limited. Future upgrades to LIGO and future detectors like the proposed LISA space observatory, which would detect gravitational waves from a completely different range of frequencies, may give us the precision we need. The window is opening, slowly, but it is opening. There is another possible observation that could shed light on the singularity question. Hawking radiation. As we discussed, Hawking showed that black holes emit a faint glow of thermal radiation. This radiation is incredibly weak for any black hole we could ever observe directly. A stellar mass black hole has a Hawking temperature of roughly a billionth of a degree above absolute zero, far too cold to detect against the cosmic microwave background, which fills the universe at about 2.7 degrees. But the radiation exists, at least in theory, and if the internal structure of a black hole is different from what the classical model predicts, then the Hawking radiation it produces may also be different. Not in amount, necessarily, but in its subtle quantum properties, in the correlations between the particles it emits, in the information it carries. If the fuzzball model is correct, then the Hawking radiation from a black hole is not truly thermal. It carries information. And in principle, if you could collect every single photon of Hawking radiation emitted over the lifetime of a black hole, you could reconstruct everything that ever fell in, every star, every planet, every grain of dust, every photon. It would all be there, encoded in the radiation. This is an extraordinary claim, and testing it is, for the moment, beyond our capabilities. But the fact that the claim can be made, that the math supports it, is itself a remarkable achievement. It shows that the information paradox has a plausible solution. It shows that the laws of quantum mechanics can be preserved, even in the extreme environment of a black hole. And it suggests strongly that the singularity is not the final word. There is also the fascinating possibility that what happens inside a black hole could be connected to dark matter, the mysterious substance that makes up about 85% of the mass in the universe. Dark matter does not interact with light. It does not glow. It does not absorb radiation. We can only detect it through its gravitational effects. And despite decades of searching, we still do not know what it is. Some physicists have proposed that dark matter could be made up of tiny, primordial black holes that formed in the very earliest moments after the Big Bang, when the density of the universe was so extreme that small regions could collapse into microscopic black holes. And if these primordial black holes do not have singularities, if they have Planck cores or some other finite interior, then they may behave differently from what we expect. They may emit particles. They may leave remnants when they evaporate. And those remnants, tiny, stable, non-radiating objects, could be the dark matter we have been looking for all along. This is still speculative, but it is the kind of speculation that connects the tiniest possible objects, quantum gravity effects at the Planck scale, to the largest structures in the universe, the distribution of dark matter across galaxies and clusters. It is a thread that links the deepest mystery inside a black hole to the deepest mystery outside of it. And pulling on that thread might unravel both mysteries at once. Let us take a moment to appreciate how far we have come. A century ago, black holes were a mathematical curiosity. 50 years ago, they were a theoretical prediction. 20 years ago, they were strongly supported by indirect evidence. And today, they are a confirmed, observed, repeatedly measured reality. We have photographed them. We have heard them collide. We have mapped the orbits of stars around them. We have watched gas fall into them in real time. The march of scientific progress has been relentless and awe-inspiring. And now, we stand at the next frontier. We know the black hole is real. We are beginning to understand what the event horizon is and how it works. And we are closing in on the most important remaining question. What is at the center? What replaces the singularity? What is the true nature of the most extreme state of matter and energy in the cosmos? The answer is still out there. It is waiting for us, waiting for better detectors, better theories, better experiments, better questions. And that is not a cause for frustration. It is a cause for excitement, because the gaps in our knowledge are not failures. They are invitations. They are open doors, waiting for someone to walk through. Science is not a collection of facts. It is a process, a way of asking questions, a way of testing ideas, a way of being wrong, recognizing that you are wrong, and finding a better answer. The singularity is one of the most productive mistakes in the history of physics. It was not wrong in the way that a broken clock is wrong. It was wrong in the way that a compass is wrong when it points you in a direction that says there is something extraordinary over there, but you need better equipment to reach it. The singularity pointed us toward quantum gravity. It pointed us toward the deepest questions about the nature of space and time. And for that, we should be grateful. Now let us go somewhere unexpected. Let us talk about heat, because one of the most surprising discoveries about black holes has nothing to do with gravity or spacetime or singularities. It has to do with thermodynamics, the study of heat, energy, and entropy. And this connection between the physics of steam engines and the physics of cosmic monsters turns out to be one of the most important clues we have about what is really going on inside. In the early 1970s, a young physicist named Jacob Bekenstein noticed something odd about black holes. According to classical general relativity, a black hole is described by just 3 numbers: its mass, its electric charge, and its spin. That is it. 3 numbers to describe an entire object. This is known as the no-hair theorem. The idea is that a black hole has no hair, no distinguishing features, no complexity. 2 black holes with the same mass, charge, and spin are identical. You cannot tell them apart. They carry no memory of how they formed, no record of what fell in, no trace of the stars and planets and civilizations that may have been swallowed up. All that information is gone, reduced to 3 simple numbers. But Bekenstein saw a problem with this. If a black hole is formed from the collapse of a star, that star was made of an enormous number of particles: electrons, protons, neutrons, each one with its own quantum state, its own position, its own momentum, its own spin. The total amount of information needed to describe the star is staggering. And according to the second law of thermodynamics, the entropy of the universe can never decrease. Entropy, in the simplest terms, is a measure of disorder, of randomness, of the number of ways a system can be arranged without changing its overall appearance. A star has enormous entropy because it is made of an enormous number of particles in an enormous number of possible arrangements. And when that star collapses into a black hole, all that entropy has to go somewhere. It cannot just vanish. That would violate the second law. Bekenstein proposed something radical. The entropy of a black hole is proportional to the area of its event horizon, not its volume, not its mass, its area. The surface area of the event horizon, measured in units of the Planck area, tells you the entropy of the black hole. And this number is enormous. A stellar mass black hole has an entropy of roughly 10 to the 77. That is more than the entropy of the star it formed from. The second law is satisfied. When the star collapses, the entropy of the universe increases, as it must. But the idea that entropy is related to surface area, not volume, is deeply strange. In everyday life, the entropy of a box of gas depends on the volume of the box. More volume, more places for the particles to be, more entropy. But for a black hole, it is the surface that matters. This led to one of the most mind-bending ideas in modern physics, the holographic principle. The holographic principle suggests that all the information contained within a region of space can be described by information on the boundary of that region. Like a hologram. A hologram is a flat, two-dimensional surface that encodes a three-dimensional image. When you look at it from the right angle, you see depth and volume and structure, even though all the information is stored on a flat sheet. The holographic principle says the universe might work the same way. All the information about what is inside a black hole may be encoded on its event horizon. The three-dimensional interior may be, in some deep sense, a projection of the two-dimensional surface. This is not just a pretty analogy. It is a mathematical result, supported by rigorous calculations in string theory. In 1997, the theoretical physicist Juan Maldacena proposed what is now called the AD-CFT correspondence, a mathematical duality between a theory of gravity in a certain type of curved spacetime and a quantum field theory on the boundary of that spacetime. The details are technical, but the implication is staggering. Gravity in the interior is equivalent to quantum mechanics on the boundary. The two descriptions are not just similar, they are identical. They are two different languages describing the same physics. And if this is true, then the singularity at the center of the black hole is not a fundamental feature of reality. It is an artifact of the gravitational description. In the quantum description, on the boundary, there is no singularity. There is only information. Encoded, scrambled, incredibly complex information, but finite information, physical information, no infinities. The holographic principle connects beautifully to the fuzzball picture. If all the information about a black hole is encoded on its surface, then the idea that the entire interior is filled with tangled strings makes sense. The fuzzball is, in a way, the holographic encoding made manifest. The surface is not a thin shell around an empty void. The surface is the object. The inside and the outside are the same thing, viewed from different angles. And the singularity, the supposed point of infinite density at the center, simply does not appear in this picture. It has been dissolved into the quantum structure of the surface. Now, let us bring all of this back to Hawking radiation and the information paradox, because the thermodynamics of black holes is where these ideas really come alive. When Hawking discovered that black holes radiate, he also showed that the radiation has a specific temperature. The temperature depends on the mass of the black hole. The more massive the black hole, the cooler it is. This is the opposite of what you might expect. A bigger black hole is colder than a smaller one. The supermassive black hole at the center of our galaxy, Sagittarius A star, has a temperature of roughly 100 trillionth of a degree above absolute zero. Absolutely frigid. A stellar mass black hole is warmer, but still incredibly cold. And a tiny black hole, one with a mass comparable to a mountain, would be searingly hot. Hot enough to glow in gamma rays. This relationship between mass and temperature has a fascinating consequence. As a black hole radiates Hawking radiation, it loses energy. And since energy is mass, according to Einstein's E equals mc squared, the black hole loses mass. And as it loses mass, it gets hotter. And as it gets hotter, it radiates faster. And as it radiates faster, it loses mass even more quickly. It is a runaway process. The black hole gets smaller and hotter and brighter, accelerating all the way down. And at the very end, when the black hole is tiny, it is blazingly hot and radiating furiously. In the final fraction of a second, the remaining mass is converted into a burst of radiation. And then the black hole is gone. At least, that is the classical picture. But what happens at the very end? When the black hole has evaporated down to a tiny remnant, what is left? In the singularity model, the answer is nothing. The singularity vanishes along with the event horizon, and all the information that was trapped inside is lost forever. This is the information paradox in its starkest form. The universe has lost information. Quantum mechanics has been violated. But in the Planck star model, the ending is very different. As the black hole shrinks, the Planck star inside gets closer and closer to the surface. Remember, the Planck star is not shrinking. It has been sitting there the whole time, at Planck density, slowly expanding from the original quantum bounce. The black hole shrinks from the outside, the Planck star grows from the inside, and eventually they meet. The event horizon dissolves, and the Planck star, carrying all the information that was ever absorbed by the black hole, is exposed. In a flash, the information is released, not destroyed, not lost, released, returned to the universe. Some physicists have proposed that this final burst could produce a distinctive signature in gamma rays, a specific pattern of high-energy radiation that we might be able to detect. If primordial black holes, formed in the early universe, are just now reaching the end of their evaporation, then we might be able to see these bursts happening right now. They would show up as brief, intense flashes of gamma radiation, different in character from the gamma ray bursts produced by supernovae or neutron star mergers. And if we found them, if we could identify even one such burst, it would be extraordinary evidence for the existence of Planck stars and against the existence of singularities. The search is ongoing. We have not found these signals yet, but we have the technology to look, and we are looking. Gamma-ray telescopes in orbit, like Fermi, are constantly scanning the sky, and as our instruments improve and our data accumulates, the chances of detection grow. Let us now consider the black hole from a completely different perspective, the perspective of the person falling in. You are an astronaut. You are drifting in space, far from any star, and ahead of you is a black hole, a big one, a supermassive black hole millions of times the mass of the sun. You point your ship toward it and begin to fall. What do you experience? First, nothing unusual. You are in free fall. The gravity pulling on your feet is almost the same as the gravity pulling on your head. You feel weightless, comfortable even. You look around and see the stars behind you, their light bent and distorted by the black hole's gravity. The star field is twisted into an eerie ring, the photons of distant stars being curved around the black hole and funneled toward your eyes. Ahead of you, the black hole itself is a region of absolute darkness. No light comes from it. It is a hole in the sky. As you get closer, the stars behind you begin to blur. The bending of light becomes more extreme. Entire galaxies are smeared into arcs. The boundary between the dark region and the bright ring becomes sharper. And still, you feel nothing. No tugging, no stretching, no warning. The event horizon is approaching, and it is invisible. You cross the event horizon. And here is the remarkable thing. Nothing happens. No flash, no bang, no wall. You drift right through it. Your instruments do not detect any change. Your body feels no different. The event horizon is not a physical barrier. It is a mathematical boundary, a line in the sand that can only be defined from the outside. From your perspective, inside there is no way to know that you have crossed it. The universe around you looks continuous and smooth. The same stars are behind you, though their light is now impossibly warped. Ahead of you is still the dark center, but now something has changed. Even though you cannot feel it, you can no longer leave. Every possible path you could take, every direction you could fire your engines, leads deeper into the black hole. The geometry of space and time itself has conspired against you. outward does not exist anymore. There is only inward. And the inward journey has a destination. In the classical model, that destination is the singularity. A point of infinite density where your body, your ship, your atoms, your quarks, your everything is crushed into zero volume. The technical term for what happens to you on the way is spaghettification. As you approach the center, the difference in gravitational pull between your head and your feet grows. At first, the stretching is gentle. Then it becomes uncomfortable, then painful, and eventually the tidal forces tear you apart. Your body is stretched into a thin stream of matter, pulled like taffy, and fed into the singularity. This is the standard picture, the grim, dramatic, terrifying picture. But if the singularity is not real, then the journey has a different ending. In the Planck star model, you do not hit a point of infinite density. You hit a region of finite but extreme density, the quantum floor, and what happens then is less clear. Perhaps the tidal forces are still devastating. You are still falling into the most dense object in the universe. But there is no point where the physics breaks down. There is no infinity. There is no place where cause and effect lose their meaning. There is, instead, a physical object, strange, extreme, unlike anything in our experience, but physical, real, governed by laws, governed by the same quantum rules that govern atoms and photons and everything else. And in the fuzzball model, the journey is different still. You may never reach the center at all, because the fuzzball fills the entire interior. When you cross what appears to be the event horizon, you are actually falling onto the surface of the fuzzball. You are absorbed into the tangle of strings. Your information is not destroyed. It is encoded, scrambled, woven into the quantum fabric of the object. From your perspective, the experience is likely indistinguishable from hitting a surface. A very hot, very dense, very quantum surface, but a surface nonetheless, not a void, not a plunge into nothing, a collision with something. Both of these pictures are less dramatic than the singularity, less terrifying, less cinematic, but they are also more honest, more consistent with what we know about the universe, more consistent with the laws of physics that have been tested and verified in every other domain. The singularity is the spectacular failure of a theory pushed beyond its limits. The alternatives are the quiet, steady work of a deeper theory, doing what physics always does, replacing the impossible with the merely extraordinary. Let us talk now about what all of this means for the future of physics, because we are living in a remarkable era, an era when the questions that were purely theoretical just a few decades ago are becoming experimental, an era when the boundary between what we know and what we do not know is shifting rapidly and dramatically. The Event Horizon Telescope continues to improve. New telescopes are being added to the array. The resolution is getting sharper. Future images of black holes may reveal features that we cannot see today. Subtle asymmetries in the shadow, fine details in the ring of light, signatures of the near-horizon environment that could distinguish between a classical black hole and a fuzzball or other alternative. The next generation of gravitational wave detectors, including the space-based LISA observatory, which is planned for launch in the 2030s, will detect gravitational waves at frequencies that ground-based detectors like LIGO cannot reach. These lower frequency waves come from the mergers of supermassive black holes, the kind at the centers of galaxies, and the signals will be incredibly rich enough potentially to reveal the internal structure of the merging objects, rich enough to detect the echoes that would distinguish a singularity from a finite core. Particle physics experiments at the Large Hadron Collider and future colliders may also provide clues. While we cannot create a black hole in a laboratory, the extreme energies achieved in particle collisions probe the same quantum realm, where gravity and quantum mechanics meet. Any signs of extra dimensions, of string-like behavior, of quantum gravitational effects at high energies, would give us evidence for or against the various theoretical frameworks. And even negative results, even the absence of expected signals, narrows the space of possibilities and brings us closer to the truth. The mathematical work continues as well. Physicists are refining their models of Planck stars, fuzzballs, and other alternatives. They are running computer simulations of collapsing stars in quantum gravity. They are deriving new predictions. They are finding new connections between the microscopic world of quantum mechanics and the macroscopic world of black holes. Each new paper, each new calculation, each new insight is another piece of the puzzle. And then there is the most ambitious goal of all, the theory of everything. The unified framework that combines general relativity, quantum mechanics, and everything in between into a single coherent description of nature. This is the holy grail of physics. And while we do not have it yet, the work on black holes and singularities is bringing us closer. Because the singularity is the point where general relativity and quantum mechanics collide most violently. It is the place where the conflict between the two theories is most acute. And resolving that conflict, understanding what really happens at the center of a black hole, is equivalent to solving the unification problem. The singularity is not just a question about black holes. It is the question about the universe. Let us take a step back now and think about what we have learned tonight. We started with a simple statement. The black hole is real. We have seen it. We have confirmed it. It is one of the most thoroughly tested predictions in all of science. And then we made a second statement. The singularity, the supposed point of infinite density at the center, is almost certainly not real. It is a mathematical artifact, a sign that our best theory of gravity has reached its limit. We explored the anatomy of a black hole. The event horizon, the point of no return, is a well-understood and well-confirmed feature of spacetime. The singularity behind the event horizon is a prediction of general relativity that has never been observed and likely does not exist. We discussed why general relativity predicts singularities. It is a classical theory. It does not account for quantum effects. And at the extreme conditions inside a black hole, quantum effects cannot be ignored. We explored the leading candidates for what might replace the singularity. Loop quantum gravity suggests a Planck star, a quantum bounce that creates a finite, dense core. String theory suggests a fuzzball, an extended object made of tangled strings that fills the entire interior. The Haywood metric provides a mathematical framework for a smooth, singularity-free black hole. And recent work from the University of Barcelona shows that these kinds of singularity-free black holes can arise from pure gravity, without exotic matter. We discussed how these alternatives resolve the information paradox, one of the deepest problems in physics. If the singularity is replaced by a physical object, information is not destroyed. It is preserved. The laws of quantum mechanics hold. Unitarity is saved. We explored the observational possibilities, gravitational wave echoes, gamma-ray signatures from evaporating Planck stars, future images from the Event Horizon Telescope, space-based detectors like LISA. Each of these represents a window into the interior of a black hole, a chance to test the theories and distinguish between the models. And we reflected on what all of this means. The singularity is not a destination. It is a detour, a wrong turn in the math that pointed us toward the right question. Or the real destination is quantum gravity. The real prize is a deeper understanding of space, time, and the fabric of reality. And we are getting closer every day. Let us now imagine what the future might look like. Imagine that one day, perhaps 10 years from now, perhaps 50, perhaps 100, we crack the code. We find the theory of quantum gravity. We understand finally and fully what happens at the center of a black hole. What would that moment look like? It might come from a gravitational wave detection, a signal from a merging pair of black holes, recorded with such precision that we can see the internal structure of the resulting object, a pattern that matches one model and rules out the others, a moment when the fuzzball echoes appear in the data, clear and unmistakable, or when the Planck star signature shows up in a gamma ray burst, confirming a prediction made decades earlier. Or it might come from a mathematical breakthrough, a new set of equations that smoothly combine general relativity and quantum mechanics, a framework that predicts the exact behavior of matter at Planck density, a calculation that shows, beyond any doubt, what the interior of a black hole looks like. Or it might come from an entirely unexpected direction, a measurement we did not anticipate, a signal from a source we did not know existed, a discovery that rewrites the rules and opens up a completely new chapter. The history of physics is full of such surprises. Hawking radiation itself was a surprise. The accelerating expansion of the universe was a surprise. Gravitational waves, when they were first detected in 2015, were a surprise not in their existence, but in their timing and beauty. However it happens, the moment will be transformative. It will be one of the greatest achievements in the history of human thought. A moment when we looked into the most extreme conditions in the universe and understood what we saw. A moment when the infinite became finite, when the impossible became merely difficult, when the singularity was replaced by something real. And that brings us to something we should not rush past. The journey of a star, because to truly appreciate what a black hole is, and why the singularity question matters so much, you need to understand where black holes come from. They do not appear out of nothing. They are born, and their birth is one of the most violent, most beautiful events in all of nature. Every black hole in the universe began its life as a star, a massive star, much heavier than our sun, at least 20, maybe 30 times the mass of the sun, and often much more. These stars burn hot and fast. Our sun will live for about 10 billion years. A star 30 times its mass might live for only 10 million years, 1,000th of our sun's lifetime. But while it lives, it is spectacular. It blazes with a luminosity that can be hundreds of thousands of times greater than the sun. It is blue-white, the hottest possible color for a star, and it pours radiation into space with an almost reckless intensity. Inside this star, the story is one of constant battle. Gravity pulls inward, always inward. From the moment the star was born, gravity has been trying to crush it, and the only thing holding it up is the energy produced by nuclear fusion at its core. The star fuses hydrogen into helium. When the hydrogen runs out, it fuses helium into carbon, then carbon into neon, neon into oxygen, oxygen into silicon. Each stage produces less energy and lasts for a shorter time. The hydrogen burning phase lasted millions of years. The silicon burning phase lasts about a day. And when the silicon is used up, When the last nuclear fuel is spent, the core is made of iron, and iron is the end of the road. Iron cannot be fused to release energy. In fact, fusing iron absorbs energy. The nuclear furnace goes out, and gravity, which has been waiting patiently for millions of years, finally wins. The core collapses in less than a second. The iron core, about the size of the Earth but with a mass greater than our Sun, falls inward at up to a quarter of the speed of light. The outer layers of the star, robbed of their support, come crashing down behind it. The collapse is so fast, so violent, so extreme that for a brief moment, the density at the center exceeds the density of an atomic nucleus. Protons and electrons are crushed together into neutrons. The core becomes a ball of neutrons, roughly 10 miles across, more dense than anything in the ordinary universe. If the star is not too massive, the collapse stops here. The neutrons push back. Their quantum mechanical properties, the Pauli exclusion principle, which forbids two identical particles from occupying the same quantum state, provide a pressure that halts the collapse. The result is a neutron star, an object that packs more mass than the Sun into a sphere the size of a city. A teaspoon of neutron star material would weigh about 1 billion tons. The surface gravity is about 200 billion times the surface gravity of Earth, and the magnetic field is 1 trillion times stronger than Earth's. Neutron stars are among the most extreme objects in the cosmos, but they are not black holes. They have stopped. They have found a flaw. Quantum mechanics has saved them. But if the star is massive enough, even neutron degeneracy pressure is not enough. The mass of the collapsing core exceeds what is called the Tolman-Oppenheimer-Volkoff limit, roughly 3 times the mass of the Sun. Above this limit, no known force can stop the collapse. Not electron pressure, not neutron pressure, not any form of quantum mechanical resistance that we know of. The collapse continues. The matter falls past the point of no return. An event horizon forms, and a black hole is born. This is the critical moment, the moment where our understanding hits a wall, because everything up to this point is well understood. The nuclear physics of stellar interiors, the mechanics of core collapse, the formation of neutron stars. All of this is supported by observation and experiment. We have detected neutron stars. We have measured their masses and spins. We have even seen them collide, producing gravitational waves and a spectacular kilonova, a burst of light from the radioactive decay of heavy elements forged in the merger. The physics of stellar collapse, up to the point of black hole formation, is solid. But once the event horizon forms, the window closes. We cannot see inside. We cannot probe the interior. And the question of whether the collapse continues all the way to a singularity, or whether some new quantum gravitational effect intervenes, is the question we have been exploring tonight. The question that sits at the intersection of everything we know and everything we do not know. Let us think about this from the star's perspective. The matter that forms the black hole was once a star. It was once hydrogen gas, floating in a nebula, billions of years ago. That gas collapsed under its own gravity. It heated up. It ignited. It burned for millions of years, forging the elements that make up planets and people. Carbon, oxygen, iron. The atoms in your body were made inside a star like this, and then the star died. Its core collapsed. And the matter that was once part of a burning living star was swallowed by the geometry of spacetime itself. Where did that matter go? In the singularity model, it went to infinity. It was crushed out of existence. Every atom, every neutron, every quark, compressed into a point of zero volume. The information about what the star was made of, about its history, about the elements it forged, about the light it emitted, was erased. Gone. Not just hidden, destroyed. And this is what makes the singularity so troubling. It is not just a mathematical problem. It is a philosophical one. The singularity says that the universe can erase its own history, that there are places where the past simply ceases to exist. But the new physics says something different. The new physics says that the matter is still there. Compressed, yes. Transformed, certainly. But there, in a Planck star, in a fuzzball, in whatever dense, finite physical object sits at the center. The information is not destroyed, it is preserved. The history of the star, the record of every atom and every reaction and every photon, is encoded in the quantum state of the object, hidden behind the event horizon, yes, inaccessible to us for now, but not gone, not erased, still part of the universe, still subject to the laws of physics, still, in principle, recoverable. This is a different kind of universe, a kinder kind, if you will, a universe that does not throw away its history, a universe where information is sacred, where the past is always, somewhere, encoded in the present, and where even the most extreme conditions do not lead to the destruction of knowledge. This is the universe that quantum gravity describes, and it is, in many ways, a more beautiful universe than the one with singularities. Let us now explore another dimension of the black hole that often gets overlooked, the way it interacts with its surroundings. Because black holes are not isolated objects sitting quietly in the void. They are active, they are hungry, and they shape the universe around them in ways that are both dramatic and subtle. When matter falls toward a black hole, it does not fall straight in, unless it is heading directly for the center, which is extremely unlikely. The matter has some sideways motion, some angular momentum, and that angular momentum causes the matter to spiral inward, like water going down a drain. The matter forms a disk, an accretion disk, and this disk is one of the most energetic environments in the entire universe. As the matter spirals inward, it is compressed, heated, accelerated. Particles in the inner regions of the disk are moving at a significant fraction of the speed of light. The temperature can reach billions of degrees, higher than the center of a star, higher than the temperature of a nuclear explosion. The disk glows with the intensity of 1 trillion suns. It emits light across the entire electromagnetic spectrum, radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays, all from a region no bigger than our solar system. Some of this energy is released as the matter slowly spirals closer to the event horizon. The gravitational potential energy of the falling matter is converted into heat and radiation with an efficiency that dwarfs nuclear fusion. A nuclear reactor converts about 1% of the rest mass energy of its fuel into usable energy. An accretion disk around a black hole can convert up to 40%. Black holes are, paradoxically, the most efficient energy generators in the universe. They do not produce energy from within. They extract it from the matter that falls toward them. And then there are the jets. Some black holes, particularly those at the centers of galaxies, produce enormous beams of material that shoot outward from the poles at nearly the speed of light. These jets can extend for thousands of light years, carrying energy and particles far beyond the black hole's immediate neighborhood. The jet from the supermassive black hole at the center of M87, the same black hole imaged by the Event Horizon Telescope, stretches for about 3,000 light years. It is visible in optical telescopes. It is one of the most dramatic structures in the universe. The mechanism that produces these jets is still not fully understood, but it is believed to involve the interaction between the black hole's spin, its magnetic field, and the accretion disk. The spinning black hole drags space-time around with it, a phenomenon called frame dragging. This twisted space-time, combined with the intense magnetic fields generated by the electrically charged particles in the disk, creates a kind of cosmic funnel. Matter and energy are channeled along the spin axis, focused into a narrow beam, and launched into intergalactic space at enormous speeds. These jets have a profound effect on the galaxy that hosts the black hole. They pump energy into the surrounding gas. They heat it. They push it around. They can suppress the formation of new stars by blowing away the raw material that stars need to form. Or, in some cases, they can trigger star formation by compressing nearby gas clouds. The supermassive black hole at the center of a galaxy is not just a passive resident. It is an active participant in the galaxy's evolution. It shapes the galaxy's growth. It regulates its star formation rate. It influences its overall structure. This is a relationship that astronomers have been unraveling for decades. There is a tight correlation between the mass of a galaxy's central black hole and the mass of the galaxy's bulge, the dense collection of stars at the center. The bigger the bulge, the bigger the black hole, and vice versa. This correlation is so tight that it cannot be a coincidence. The black hole and the galaxy must have grown together, each one influencing the other, each one shaping the other's evolution. The black hole eats gas and grows. The jets and radiation from the black hole push gas away and slow the galaxy's growth. It is a feedback loop, a cosmic dance, and it has been going on for billions of years since the earliest days of the universe. Understanding this feedback loop is one of the most active areas of research in astrophysics, and it connects, indirectly but importantly, to the singularity question, because the way a black hole interacts with its surroundings depends on its properties, its mass, its spin, its magnetic field, and potentially its internal structure. If the interior of a black hole is a singularity, the physics of the accretion and jet formation follows one set of rules. If the interior is a fuzzball or a Planck star, the physics might follow slightly different rules. The differences would be subtle, but they might be detectable. One fascinating area of research involves the behavior of material very close to the event horizon. In the classical model, the event horizon is a perfectly smooth mathematical boundary. But if the fuzzball model is correct, the surface is not smooth. It is fuzzy. And incoming matter would interact with this fuzzy surface in ways that are slightly different from the classical prediction. These differences could show up in the spectrum of radiation emitted by the accretion disk, in the timing of X-ray pulses, in the polarization of light near the event horizon. The Event Horizon Telescope is already measuring polarization patterns around M87 and Sagittarius A star. Future observations may be precise enough to detect the subtle signatures of a quantum surface. This is the beauty of modern astrophysics. We are no longer limited to distant theorizing. We have tools, real tools, telescopes that span the Earth, gravitational wave detectors that can measure distortions smaller than a proton, gamma-ray satellites that scan the entire sky, supercomputers that can simulate the violent collisions of black holes. The gap between theory and observation is narrowing, and the answers are waiting for us, encoded in the light and waves that reach us from the most extreme objects in the cosmos. Let us return now to the human dimension of this story, because science is, at its core, a human endeavor. It is driven by curiosity, by wonder, by the refusal to accept that something is unknowable. And the story of the singularity is a story about that refusal. For decades, the singularity was treated as a kind of full stop. The end of the road, the place where physics gives up. Many scientists simply shrugged and moved on. The singularity is behind the event horizon, they said. We can never see it. We can never test it. So what does it matter? And for a practical, observational science like astronomy, there was some logic to that attitude. Why worry about something you can never observe? But the theorists did not give up. They worried. They poked at the problem. They asked uncomfortable questions. What if the singularity is telling us something important? What if its very impossibility is a clue? What if the breakdown of the equations is not a dead end, but a starting line? And they were right. The singularity is a clue, the most important clue we have. It tells us exactly where our understanding fails. It tells us exactly where we need to look. And it tells us exactly what kind of theory we need to build. The history of physics is full of these moments. Moments when an impossibility turned out to be a signpost. The ultraviolet catastrophe led to quantum mechanics. The failure of the Michelson-Morley experiment led to special relativity. The orbit of Mercury, which did not match Newton's predictions, led to general relativity. And the singularity at the center of a black hole may lead us to the next great revolution. The theory of quantum gravity. Every great theory in physics has been born from a crisis, from a moment when the old theory stopped working and something new was needed. And we are in such a moment right now. The crisis is the incompatibility of general relativity and quantum mechanics. The symptom is the singularity, and the cure is still being formulated. But the ingredients are coming together. Loop quantum gravity, string theory, the holographic principle, the Planck star, the fuzzball. Each of these is a piece of the puzzle. And the puzzle is being assembled, slowly but surely, by thousands of physicists around the world. We may not see the final answer in our lifetimes. Or we might. The pace of discovery in physics has been accelerating. The tools are getting better. The data is getting richer. The ideas are getting sharper. And the next breakthrough could come from anywhere. From a young graduate student writing equations in a notebook. From a team of experimenters analyzing data from a gravitational wave detector. From a computer simulation that reveals an unexpected pattern. The universe is not hiding its secrets. It is revealing them one by one to anyone patient and clever enough to look. There is another effect of black holes that deserves our attention. An effect that is not just scientifically fascinating but visually stunning. Gravitational lensing. When light from a distant star or galaxy passes near a black hole, the curved spacetime bends the light's path. The star appears to shift position. And if the alignment is just right, the light can be bent so dramatically that it wraps around the black hole entirely. You see the same star in multiple locations at once. Rings of light, arcs of light, distorted, stretched, duplicated images of distant objects painted across the sky by the brush of gravity. Einstein himself predicted this effect in 1936, and it has been observed countless times since then. Massive galaxies bending the light of more distant galaxies behind them, creating beautiful arcs and rings, known as Einstein rings. But near a black hole, the effect is extreme. Light can orbit the black hole multiple times before escaping, creating a photon sphere, a region where light itself is trapped in a circular orbit. Any photon that enters the photon sphere at exactly the right angle will loop around the black hole forever, neither falling in nor escaping. It is a razor-thin boundary. And just outside it, photons can complete 1, 2, or even many orbits before being flung outward to reach a distant observer. These photons carry information about the space-time geometry very close to the event horizon. They are our best window into the extreme gravitational environment of a black hole. The Event Horizon Telescope has already detected hints of this photon ring in its images of M87 and Sagittarius A star. The bright ring in the images is not just the accretion disk seen head-on. It is a combination of light from the disk and light that has orbited the black hole, been bent and focused by gravity, and then escaped toward Earth. By studying the structure of this ring, its thickness, its brightness profile, its polarization, astronomers can test general relativity in the strong field regime. They can measure the spin of the black hole. They can probe the magnetic field structure near the horizon. And they can look for deviations from the classical predictions that might hint at a quantum, gravitational interior. This is one of the most active areas of observational black hole physics today. New algorithms are being developed to extract more information from the existing data. Future observations, with more telescopes and higher frequencies, will sharpen the images further. And every new detail, every new pixel, every new measurement brings us closer to understanding not just what the black hole looks like from the outside, but what is happening on the inside. Time dilation near a black hole is another phenomenon that defies everyday intuition. We discussed earlier how a falling observer crosses the event horizon without noticing. But from the perspective of a distant observer, the story is very different. As you watch someone fall toward a black hole, you see them slow down. Their clock, visible through a telescope, ticks more and more slowly. Their movements become sluggish. Their light becomes redder and dimmer, as each photon they emit loses energy climbing out of the gravitational well. And as they approach the event horizon, the slowing becomes extreme. From your perspective, they never quite reach it. They freeze. Their image becomes a faint red ghost, hovering at the edge of the shadow, dimming asymptotically toward invisibility. You never see them cross. They are forever on the threshold. This is not a paradox. It is simply a consequence of how time works in curved spacetime. Time passes at different rates in different gravitational fields. A clock on the surface of the Earth ticks slightly slower than a clock in orbit. A clock near a black hole ticks far slower than a clock far away. And at the event horizon itself, the time dilation is, in principle, infinite. From the outside, nothing ever crosses the horizon. From the inside, the crossing is instantaneous and unremarkable. Both perspectives are valid. Both are correct. They are simply different views of the same physical reality, seen from different locations in curved space-time. This difference in perspective is central to many of the puzzles of black hole physics. The information paradox, for example, looks different depending on whether you are inside or outside the black hole. From the outside, information appears to be trapped forever behind the event horizon. From the inside, the information is right there, falling alongside you. The holographic principle attempts to reconcile these two views by saying that the information exists in both places simultaneously, encoded in the quantum state of the horizon itself. Whether this is the correct resolution remains to be seen. But the idea that perspective matters, that the same physical event can look completely different to different observers, is one of the deepest lessons of general relativity. And it may be the key to understanding what happens at the center. Let us now revisit one of the most important chapters in the story of black holes, the moment when they went from being theoretical to real. because for most of the 20th century, black holes were considered exotic mathematics, interesting on paper, but possibly irrelevant to the actual universe. It took decades of accumulating evidence to change that view, and the evidence came in stages, each one more convincing than the last. The first strong candidate for a real black hole was discovered in 1964, an X-ray source in the constellation Cygnus, catalogued as Cygnus X. 1. X-ray telescopes, which were just coming into use at the time, detected an incredibly powerful source of X-ray radiation coming from this region of the sky. Further observations revealed that the X-rays were coming from a binary system, a pair of objects orbiting each other. One was a massive blue star, visible to optical telescopes. The other was invisible, dark, but incredibly heavy. And the X-rays were being produced by material from the blue star being stripped away and pulled toward the invisible companion, heated to millions of degrees as it spiraled inward. The invisible companion had to be compact, it had to be massive, and it had to be small enough that material falling toward it could reach the extreme temperatures needed to produce X-rays. The best explanation was a black hole. This was not proof. Not yet. The mass of the invisible companion was estimated at around 15 times the mass of the Sun, well above the limit for a neutron star. But there were uncertainties. The measurements were indirect, and some physicists held out hope that some other kind of exotic object could explain the observations. Stephen Hawking himself, in a now famous bet with fellow physicist Kip Thorne, wagered that Cygnus X1 was not a black hole. He lost the bet, and he conceded it gracefully in 1990 as the evidence continued to mount. Through the 1980s and 1990s, more black hole candidates were found, in binary systems, where one star feeds mass to an invisible, massive companion. In the centers of galaxies, where stars orbit at tremendous speeds around invisible points of enormous mass. The supermassive black hole at the center of our own galaxy, Sagittarius A star, was identified through the painstaking work of Andrea Ghez and Reinhard Genzel, who tracked the orbits of individual stars around the galactic center for decades. They showed that the stars were orbiting something 4 million times the mass of the Sun, concentrated in a region smaller than our solar system. The only known object that fits this description is a black hole. Ghez and Genzel shared the Nobel Prize in Physics in 2020, alongside Roger Penrose for this work, and then came the images. The Event Horizon Telescope's photograph of M87 star in 2019, followed by Sagittarius A star in 2022. These were not just scientific milestones, they were cultural events. The image of M87's black hole appeared on the front page of every major newspaper in the world. It then became an icon, a symbol of human curiosity and ingenuity. And it confirmed, in the most visceral way possible, that black holes are real, that these theoretical objects, born from the mathematics of a century earlier, actually exist. They sit at the centers of galaxies. They bend light and warp time. They are part of the furniture of the universe. But the images also did something else, something more subtle. They made the question of the interior more urgent. Because now we know the outside. We have seen it, we have measured it, we have confirmed it. And the natural next question is, what about the inside? What is behind the shadow? What lies beyond the glowing ring? The singularity or something else? This is where we are today, at the boundary between what has been observed and what is yet to be discovered, at the edge of knowledge, looking inward. And the view from here is exhilarating. Let us talk about Stephen Hawking for a moment, because his contributions to this story are immense and often misunderstood. Hawking was not just a popularizer of black hole physics, he was one of its architects. His work in the 1970s on black hole thermodynamics was groundbreaking. He showed that black holes have a temperature. He showed that they radiate. He showed that they can evaporate. And in doing so, he created one of the most important problems in theoretical physics, the information paradox. But he did something else too. He showed that black holes are not just gravitational objects. They are quantum objects. They live at the intersection of gravity and quantum mechanics, and understanding them requires understanding both. Hawking's approach was characteristically bold. He took the equations of quantum field theory, which describe how particles behave in empty space, and he applied them to the curved spacetime near a black hole's event horizon. What he found was that the curved spacetime causes the quantum vacuum to produce particles, pairs of virtual particles, one with positive energy and one with negative energy, are constantly popping in and out of existence everywhere in space. Normally, they annihilate each other almost instantly. But near the event horizon, something different happens. One particle falls into the black hole. The other escapes. The escaping particle carries energy away from the black hole. And from the outside, it looks like the black hole is radiating. This is Hawking radiation. And while it has never been directly observed, its theoretical underpinnings are so solid that virtually all physicists accept it as real. The temperature of this radiation is inversely proportional to the mass of the black hole. Big black holes are cold. Small black holes are hot. And as we discussed, this leads to the slow evaporation of the black hole over an almost incomprehensible timescale. A stellar mass black hole would take roughly 10 to the 67 years to evaporate. That is far, far longer than the current age of the universe. For all practical purposes, stellar mass black holes are permanent fixtures of the cosmos. But in principle, they are mortal. They will die. And the question of what happens at the end, when the last bit of mass is radiated away, is intimately connected to the singularity question. In the singularity model, the evaporation ends with a bang. The singularity is exposed. The information is destroyed. The laws of physics are violated. But in the Planck star model, the evaporation ends with a release. The information is returned. The laws are preserved. Physics wins. Now consider something fascinating. The connection between the temperature of a black hole and the curvature of spacetime near its event horizon. The temperature is determined by the surface gravity, which is related to how quickly the gravitational field changes near the horizon. The more rapidly the field changes, the higher the temperature. And this surface gravity depends on the internal structure of the black hole. If the interior is a singularity, the surface gravity has one value. If the interior is a Planck star or a fuzzball, the surface gravity may be slightly different. And if the surface gravity is different, the Hawking temperature is different. And if the Hawking temperature is different, the evaporation rate is different. This means that the internal structure of the black hole leaves a fingerprint on the Hawking radiation. A subtle, incredibly faint fingerprint, but a fingerprint nonetheless. We cannot measure this fingerprint with current technology. The Hawking radiation from any astrophysical black hole is far too faint to detect. But the mathematical framework is in place. The predictions have been made. And if one day we find a way to amplify or simulate these effects, the fingerprint could be read. The internal structure could be revealed. Not by looking inside the black hole, but by carefully studying the radiation that leaks out. This is one of the themes that runs through all of modern black hole research. We cannot look inside, but we can listen. We can detect. We can infer. The black hole hides its secrets behind the event horizon, but it also whispers them to the universe, in the faint glow of Hawking radiation, in the reverberations of gravitational waves, in the subtle patterns of light and shadow captured by our telescopes. The secrets are there. We just need to learn how to hear them. And this brings us to a thought that is both humbling and uplifting. We are the first generation in the history of life on this planet to have the tools to ask these questions. The first generation to photograph a black hole. The first generation to hear the collision of two black holes from 1 billion light years away. The first generation to have serious, mathematically rigorous theories about what happens at the center. We are standing on a threshold, and the view from here is breathtaking. Think about what it means to photograph a black hole, 55 million light years away. That light, the light that formed the image of M87, left the galaxy when dinosaurs still roamed the Earth. It traveled across 55 million light years of space, past countless stars and galaxies and voids, and arrived at our planet, where it was collected by 8 radio telescopes and assembled, pixel by pixel, into the first image of an event horizon. This is not just a scientific achievement. It is a testament to the human spirit, to the idea that no distance is too great, no mystery too deep, no challenge too daunting for a species that refuses to stop asking questions. And the questions we are asking now, about the singularity, about quantum gravity, about the true nature of the center of a black hole, are the most profound questions we have ever asked. They are questions about the foundations of reality, about the nature of space and time, about the limits of knowledge and the boundaries of the knowable. And we are making progress, real, tangible, measurable progress. The gap between what we know and what we need to know is shrinking. Every new detection, every new calculation, every new observation brings us closer. The singularity was a wall, but walls are for climbing, and the physicists of the 21st century are climbing it, with mathematical rigor and experimental precision, and the unwavering conviction that the universe makes sense. All the way down, even at the center of a black hole. Let us carry this thought forward, into the night, into the quiet, into the vast, dark, beautiful space between the stars. The universe is enormous, incomprehensibly so, and within it, at the hearts of billions of galaxies, sit the most extreme objects nature has ever produced. Black holes, real, confirmed, magnificent, and at their centers, not a breakdown, but a breakthrough waiting to happen. Not an ending, but a beginning. Not a singularity, but a story that is still being written by us. And so we arrive at the heart of the matter, the center of the black hole, the place where the singularity was supposed to be. And what do we find there? Not infinity, not a mathematical breakdown, not the end of physics, but a question, the most exciting question in all of science, and the beginning of a new chapter. Let us bring together everything we have explored tonight and paint a new picture. A picture of a black hole without a singularity. A picture that is consistent with what we know, honest about what we do not know, and open to what we might discover. Start from the outside. Far from the black hole, space is normal, flat, calm, stars shine, planets orbit, light travels in straight lines. You would never know a cosmic monster lurked nearby, but as you move closer, the curvature of spacetime begins to reveal itself. Light bends, time slows, the gravitational pull increases, and if you had instruments sensitive enough, You could measure the distortion. You could map the curve. Closer still, you reach the accretion disk, a swirling maelstrom of gas and dust and plasma, heated to temperatures that make the surface of a star seem cool by comparison. This is the furnace of the cosmos, the most efficient energy source in the universe. Light blazes from its surface. X-rays streak into space. Magnetic fields twist and writhe. And at the poles, twin jets of matter punch outward at nearly the speed of light, carving their way through the galaxy. Closer still, you approach the event horizon, the point of no return, the boundary beyond which nothing, not even light, can escape. From the outside, this boundary is invisible. It is defined not by any physical structure, but by the geometry of spacetime itself. Cross it, and your fate is sealed. But you would not feel it. You would not see it. You would drift past it like a boat crossing the equator. The line is real, but it has no physical presence. And now, inside. In the old picture, there is nothing between the event horizon and the singularity. Just empty, curved space, with all matter and energy funneling inexorably toward the central point. A void with a mathematical monster at the bottom. But in the new picture, the interior is not empty. It is full of quantum gravitational structure, full of compressed matter and tangled strings, full of the remnants of everything that ever fell in. In the Planck star model, the collapsing matter hit the quantum floor and bounced. The bounce is still happening. Frozen in time from our perspective, the Planck star sits at the center, incredibly dense, incredibly small, but finite. It has a volume, a size, a boundary. The matter that makes it up is in a quantum gravitational state, governed by laws we do not yet fully understand. But it is there. It is physical. It is real. And it carries the information of everything that was ever swallowed by the black hole. Every star, every photon, every grain of dust, all encoded in the quantum state of this tiny, extraordinary object. In the fuzzball model, there is no clear distinction between the center and the surface. The entire interior is the fuzzball, a vast, extended, incredibly complex tangle of fundamental strings, each string vibrating in its own mode, each vibration encoding information. The fuzzball is not just at the center. It fills the space. It is the black hole. From the outside, it looks like a classical black hole. From the inside, it is a solid, or solid-like, object, dense, hot, quantum, but not singular, not infinite, not broken. In the pure gravity model developed by the Barcelona team, the interior is a smooth region of extreme but finite curvature. The modifications to Einstein's equations predicted by quantum gravity prevent the curvature from reaching infinity. The matter settles into a stable, ultra-dense configuration. The equations make sense. The physics works. The thermodynamics is consistent. And the singularity simply never forms. Each of these models tells a slightly different story about the center of the black hole. They differ in the details. They differ in the mechanisms. They differ in their predictions, some of which may be testable in the coming decades. But they agree on the essential point. The singularity is not real. The center of a black hole is not a place where physics breaks down. It is a place where physics gets interesting. It is a place where the familiar rules of general relativity hand off to the deeper, stranger, more wonderful rules of quantum gravity. It is a transition, not a termination. A door, not a wall. And on the other side of that door lies a new understanding of the universe. This is the vision that is emerging from the frontier of modern physics. A black hole that is real, confirmed, observed, and understood from the outside. And a black hole that, on the inside, harbors not a mathematical absurdity, but a physical marvel, an object so dense, so hot, so extreme that it pushes the laws of nature to their very limits, but not beyond. Never beyond. The laws hold, the rules apply, even here, even at the center of the most extreme object in the cosmos. There is a certain comfort in that, a certain peace. The universe, for all its strangeness, for all its violence and extremity, is not arbitrary. It is not chaotic. It is governed by laws. And those laws, whatever their final form, are consistent. They do not break. They do not fail. They just get more interesting. Let us reflect on what this journey has taught us about science itself. Because the story of the singularity is not just a story about black holes. It is a story about how we learn, how we discover, how we get things wrong and then get them right. Science is often presented as a march of progress, a straight line from ignorance to knowledge. But the real story is messier than that. It is full of wrong turns and dead ends and beautiful mistakes. The singularity is one of those beautiful mistakes. It was a prediction of one of the greatest theories ever devised. It was mathematically rigorous. It was logically inescapable within its framework, and it was almost certainly wrong. But being wrong was not a waste. Being wrong was the point. The singularity told us exactly where our understanding failed. It told us exactly what kind of new physics we needed. It drew a giant red circle on the map of the unknown and said, "Start here." And physicists started there. They built loop quantum gravity. They built string theory. They proposed Planck stars and fuzzballs and holographic principles. They spent decades working on the problem, and they are making progress. Real, measurable, testable progress. That is how science works, not by being right all the time, but by being wrong in productive ways, by finding the places where the theories fail and using those failures as stepping stones to deeper truths. The ultraviolet catastrophe was wrong, but it led to quantum mechanics. The orbit of Mercury was wrong, according to Newton, but it led to general relativity. And the singularity is wrong, but it is leading us to quantum gravity. This is, to me, one of the most inspiring aspects of the scientific enterprise. The willingness to be wrong, the courage to admit that we do not have all the answers, and the determination to keep looking, keep testing, keep building until we do. Science does not demand perfection. It demands honesty. It demands rigor. And it demands the humility to recognize that our current understanding is always provisional, always subject to revision, always open to improvement. The singularity is being revised. It is being improved upon. It is being replaced by something better. And the something better is not just a more accurate description of a black hole. It is a more accurate description of the universe, of space, of time, of the fundamental fabric of reality. The stakes could not be higher, and the reward could not be greater. Now, let us bring this journey to a close. We have traveled far tonight. We have gone from the familiar pull of gravity on the surface of the Earth, through the warped space-time of Einstein's universe, past the event horizon of a real, observed, confirmed black hole, and into the deepest, most extreme conditions that nature allows. We have met the singularity, the mathematical phantom at the center of it all, and we have seen it dissolve, not into nothing, but into something better, something finite, something physical, something real, something that respects the laws of physics rather than violating them. The black hole is real. This is beyond doubt. We have seen its shadow. We have heard its mergers. We have measured its pull. The event horizon is real. The mass is real. The spin is real. The jets and the accretion disks and the gravitational waves are all real. But the singularity, the supposed point of infinite density at the very center, is almost certainly not real. It is a sign that our best theory of gravity is incomplete, a placeholder for a deeper truth, a question disguised as an answer, and the answer, when it finally comes, will transform our understanding of the universe. It will tell us whether space is smooth or grainy, whether time has a beginning or a bounce, whether information can ever be truly destroyed, whether the laws of physics hold everywhere, in every condition, at every scale. The center of a black hole is the final frontier, and we are going there, not with rockets, not with spaceships, but with mathematics and observation and the relentless, beautiful, stubborn curiosity that has driven science forward for centuries. If you look up tonight, you will see the stars, thousands of them scattered across the sky like diamonds on velvet. And behind those stars, beyond the reach of your eyes, lie galaxies, billions of galaxies, each one with a supermassive black hole at its heart, each one a laboratory for the most extreme physics in the cosmos, each one carrying a secret at its center, a secret that we are just now beginning to unravel. The universe is not a place of infinite mystery. It is a place of infinite wonder. There is a difference. Mystery implies the unknowable. Wonder implies the not yet known. And the story of the singularity is a story about moving from mystery to wonder, about replacing the impossible with the extraordinary, about discovering that the most extreme places in the universe are not beyond understanding. They are simply beyond our current understanding. And we are closing the gap. Black holes will keep forming. Stars will keep dying. Gravity will keep bending space and time into impossible shapes. And physicists will keep working, keep questioning, keep calculating. Keep pointing their telescopes at the sky and their equations at the unknown. Because that is what humans do. We explore. We ask. We refuse to accept that something is unknowable. And every time the universe throws up a wall, we find a way through it, or around it, or over it. We have been doing this for 10,000 years, and we are not going to stop now. The singularity was a wall, a place where the math broke and the physics stopped, and the textbooks went blank. But it is not a wall anymore. It is a door, and behind that door, something extraordinary is waiting. We do not know exactly what it is, not yet, but we know it is there. We know it is real. We know it is finite and physical and comprehensible. And we know, with the certainty that comes from 100 years of tested, confirmed, battle-hardened physics, that we will find it. So rest easy tonight. Let the stars spin above you. Let the galaxies turn. Let the black holes sit in their cosmic thrones, wrapping space-time around themselves like dark robes. They are not the end of the story. They are not the edge of the map marked, "Here be dragons." They are the next chapter, the most exciting chapter. And we are only just beginning to read it. The black hole is real. The singularity is not. And what replaces it might just be the most beautiful discovery science has ever made. Thank you for joining me on this journey through the cosmos. If this video helped you see the universe a little differently, give it a like and subscribe to Cosmic Drift for deep space journeys. We have so many more journeys ahead. Until next time, keep looking up. And now, let yourself drift. Let the stars fade into the soft black of night. Let the hum of the cosmos settle over you like a blanket. The black hole is out there, immense, patient, spinning in the dark. But it is not a mystery anymore. It is a challenge, and challenges are what we are made for. Close your eyes, breathe deeply, and let the quiet, gentle enormity of the universe carry you into sleep. The cosmos will be here when you wake,